The central limit theorem is a super powerful tool, but we need to know things about the population in order to be able to use it. Unfortunately, we don't always know things about the population, and so we need to be able to look at a sample and to figure some things out from that. So one thing that we might want to know about a sample is if the variance of our sample is actually reasonable. Like, do we think that the population variance would be similar to that variance, that sample variance, or not? So we can actually do that using the chi-square distribution. So we can take our variance and we can use an equation to then see if we have reason to believe whether our population variance would actually be different than what our sample variance is. So when we're taking a look at sample variances and trying to use those to tell us something about population variances, we have a theorem that's useful for us. So this theorem says that if the sample variance is the variance of a random sample of size n taken from a normal population having a population variance, then we get this chi-square statistic. And it's going to have a chi-square distribution with n minus 1, that's the sample size minus 1, degrees of freedom. So let's take a look at an example. We have a manufacturer of car batteries that's guaranteeing that the batteries will last on average 3 years with a standard deviation of 1 year. So if we have 5 of these batteries, they have lifetimes of 1.9, 2.4, 3.0, 3.5, and 4.2 years. We want to know if the manufacturer should be convinced that the batteries have a standard deviation of 1 year. So we're going to assume that the battery lifetime follows a normal distribution, and then we're going to use the tools that we've just learned to do this. So in order to test this idea that the population standard deviation is 1 year, or the population variance is 1 year squared, so 1 year still, what we first need to do is find the sample variance. So we can do that by using Theorem 8.1, and that tells us that our sample variance is 0.815, which is less than 1 year, but we should see if it's reasonable using this chi-square statistic that we have. So we're going to use the chi-square statistic. We have n minus 1 times our sample variance divided by the population variance that we believe is true. So our chi-square statistic is going to be 3.26. Now this chi-square statistic of 3.26 may or may not seem meaningful. It probably doesn't seem meaningful to you at this point, and that's okay. All right. There's a table at the back of your book, table A5. It's 2 tables after the normal distribution one. So this table is organized so that there's a row for each of the possible degrees of freedom. And so we're going to look at the row for 4 degrees of freedom. We got that by taking our sample size of 5 and subtracting 1 from it. So looking at the row for 4 degrees of freedom, it starts on one page and then you have to flip the page to see the rest of the row. So we're going to see that 3.26 falls between the alpha values of 0.7 and 0.5. Well, then there's the question of what do these alpha values mean, and what is that good? Is that bad? Well, it's good. It's kind of saying that 3.26 falls pretty near the middle. But the way that we end up usually using these things and reporting them is something more along the lines of saying 95% of the chi-square values with 4 degrees of freedom fall between 0.484 and 11.143. Now those two values were found by taking a look at 0.225 and 0.975 as the 2 alpha values, and then looking at that degree 4 degrees of freedom row and seeing what chi-square values were there. So take a look at that, see if you can duplicate it. So saying 95% of the values fall between those two values, our 3.26 is certainly between those two values. So we have that our variance, our population variance of 1, is reasonable. So the manufacturer has no reason to suspect that the standard deviation is anything other than 1 year. And that's how problems like this work. Another tool that we have at our disposal for when we don't meet the qualifications of the central limit theorem, either our sample size is too small or we don't know the things about the population that we need to know, is called the t-distribution. So the t-distribution allows us to use the sample standard deviation, sample mean, to make estimates. It also allows us to make estimates when the sample size is less than 30. So we can make use of this t-distribution instead of making use of our normal distribution in those cases. So I want to show you this theorem related to the t-distribution just because it's a good thing for you to see. The amount that you're actually going to have to use this theorem directly is pretty minimal. So the theorem says that we have a standard normal random variable z and a chi-square random variable v. Remember, chi-square random variables don't have to look normal. They can be kind of more skewed. And this chi-square random variable has v degrees of freedom. If z and v are independent, then we can make a distribution of a random variable t, where t equals z divided by the square root of our random variable v divided by its number of degrees of freedom. And we've got this beautiful density function. It's got some gamma functions in there and everything. And that's what the t-distribution is. So the t-distribution incorporates some parts of the normal distribution, but it also incorporates in some of this chi-square distribution as well. So it allows us to look at distributions that have slightly different shapes than a normal distribution. This calculation for t is going to be a much more commonly used thing for you. So to calculate t, what you're going to be doing is taking the sample mean of a random variable, subtracting the population mean, and dividing by the sample standard deviation divided by the square root of the sample size. Now, bringing together that calculation of t along with the theorem that we had, what we have here is this t value that we've calculated actually has a t-distribution, and it has n minus 1, so your sample size minus 1 degrees of freedom. So let's take a look at an example of this. Say we want the t value with v equals 14 degrees of freedom. That's going to leave an area of 0.025 to the left, and therefore 0.975 to the right. So you get from one of those to the other just by taking 1 minus the 0.025. That gives us the 0.975. Now, when we're notating the t-distribution, the t-values, we use a little subscript, and we subscript the area that we want to be to the right of the t-value that we're finding. So this is saying I want the t-value that has 0.975 to the right. Now, since the t-distribution is symmetric around the population mean, the same way the normal distribution is, then we know that t sub 0.975 is equal to negative t sub 0.025. So we can just take that negative sign, throw it up there, and have the 1 minus happen in our subscript. Now, if we use table A.4, This is the t-distribution table. It comes after the normal distribution table and before the chi-square distribution table. What we do is, similar to the chi-square distribution table, we go down to the row that corresponds to 14 degrees of freedom, and then the columns are labeled by alpha values. So we go to the alpha value of 0.025, and when we go over to that, we find in the table that the t-value is negative 2.145. So take a look at the table, see if you can follow along, and do that, find that value. You'll notice that the t-distribution table, like the chi-square one, the rows go across, and then you flip the page, and you're still on those same rows going across further. And you'll also notice that the t-distribution table doesn't have alpha values above 0.5. I think 0.4 is actually the maximum value that you get. That's because of the symmetric relationship, so that we can just take the negative and do 1 minus in our subscripts, and then we never need anything larger than 0.5 as a subscript, as an alpha value there. So take a look at that table, try and familiarize yourself with it, and you'll get some practice using it. It'll be good. So I want to take a look at a place that we might use a t-distribution. So here we have a situation where a chemical engineer claims that the population mean yield of a certain batch process is 500 grams per milliliter of raw material. So to check this claim, he samples 25 batches each month. If the computed t-value falls between negative t sub 0.05 and t sub 0.05, he's satisfied with this claim. So basically, it's falling, so we've got 90% of the area around 500 claimed. So 90% of the samples that we take of size 25 should fall within this range if the true mean is 500 grams. That's what he's checking. That's what he's looking for. All right. So what we're asked is, what conclusion should he draw from a sample that has a mean of 518 grams per milliliter and a sample standard deviation of S equals 40 grams? Now, we're going to assume the distribution of yields is approximately normal. So we've got a symmetric distribution. So using table A.4 again, and to calculate our degrees of freedom, we're going to take our sample size minus 1, so we'll have 25 minus 1, or 24 degrees of freedom. So we'll go to the 24 column for degrees, or 24 row, sorry, for degrees of freedom, and we're going to find t sub 0.05 by going over to the alpha 0.05 column in our degrees of freedom equals 24 row, and we'll see that the t-value there is 1.711. Now, we need to calculate the t-value of the sample that we found. So the t-value of the sample we found is 518 grams for our sample mean minus our population mean of 500 grams divided by our sample standard deviation of 40 grams divided by the square root of our sample size of 25. So when we do this arithmetic, we end up with a t-value of 2.25 for the sample. Now, since 2.25 is outside of the acceptable range of negative 1.711 to 1.711 that the engineer was hoping for, he's not satisfied that the population mean is actually the 500 grams per milliliter. Now, if we take a look at table A.4 with our 24 degrees of freedom, and we look in that row for a t-value of 2.25, we see that 2.25 falls between alpha values of 0.02 and 0.015. So this means that the probability of getting a sample of size 25 with a mean of 518 grams per milliliter, given that our actual population mean is 500 grams per milliliter, getting a sample size or sample mean of 518 or greater is actually less than 2%. This is very unlikely to happen. So consequently, the actual mean yield is likely greater than 500. So even though the engineer is not satisfied that the actual mean is 500, he might be happy because the process might be more efficient than he actually believes it to be.